Complex numbers, rectangular to polar and back again. Complex numbers are usually either represented in rectangular coordinates or in polar coordinates. We use these two representations because one is easier for algebraic operations like addition and subtraction, while the other is more convenient for operations such as multiplication and division. We graphically represent complex numbers as points on a plane, either by specifying the x and y coordinates, or by specifying the distance of the point from the origin and the angle that that line to the origin makes with the positive ray of the x-axis. To convert a complex number in rectangular coordinates to polar coordinates, the first step is to multiply and divide by the square root of x squared plus y squared. This factor is known as the modulus of the complex number. The other factor is a complex number that graphically lies on a circle of radius 1. And hence the location of this point can be specified by a single angle. First, say that the point on the circle lies in the first or second quadrant, that is, where the y-coordinate is non-negative. Then, since the cosine of the angle is equal to the x-coordinate, then the angle must be the arc-cosine of the x-coordinate. Since the range of the arc-cosine function is between 0 and pi, this function gives one angle whose cosine and sine have the correct x and y coordinates, and all angles that have this property will differ by a multiple of 2 pi. Now let's say the point on the unit circle lies in the third or fourth quadrant. In this case, the y-coordinate is less than 0. The angle alpha made with the positive ray on the x-axis is equal to minus of the arc-cosine of the x-coordinate. And every angle whose cosine and sine have the correct x and y coordinates differ from this angle by a multiple of 2 pi. Here I have listed some values of the arc-cosine function and some trig identities that might be useful for computing with complex numbers. In summary, we have that a complex number in rectangular coordinates is equal to the square root of x squared plus y squared times cosine of alpha plus I times sine of alpha, where alpha is either the arc-cosine or the negative arc-cosine of x over the square root of x squared plus y squared plus a multiple of 2 pi. If we let r equal the square root of x squared plus y squared, then we can write z equals r times e raised to the I times alpha. Of course, to go back from the polar form to rectangular coordinates, we replace e raised to the I times alpha by cosine alpha plus I times sine alpha. Then z is equal to x plus I times y, where x is r times cosine alpha and y is r times sine alpha.